Hello friends, welcome back to Let's Do Mathematics. Today we are diving into a super powerful tool in mathematics, Laplace Transform. If you have ever wondered how engineers solve complex differential equations so easily, this is magic behind it. So stay tuned till the end because by today you will not only know what a Laplace transform is but also how to calculate it for simple functions. So what is the Laplace transform? Alright, let's start with definition. Suppose we have a function ft defined for all t greater or equal to 0. Its Laplace transform is given by L of ft is equals to 0 to infinity e raised to integral from 0 to infinity e raised to power minus st ft dt. This formula looks heavy, but don't worry. It simply means we are converting a function of time ft into a new function capital Fs. Here is the function of time and we are converting it into a new function Fs which depends on the variable x. Think of it like this. Laplace transform is a bridge from the time domain to the frequency domain. Now we have a question. Does Laplace transform always exist? Great question. The answer is no. Not every function has a Laplace transform. For it to exist, two conditions must be satisfied. Let's see the two conditions. The two conditions are the Laplace transform of the function ft exists when the following conditions are satisfied. Ft is a piecewise continuous and ft is continuous in every subinterval and ft has finite limits at the end points of each subinterval. If the function satisfied, if this condition is satisfied, and another condition is ft is of exponential order of alpha, that is there exists a positive real number capital M such that absolute value of ft must be less than or equal to m times of e raised to power alpha t for all t greater or equal to 0. And in other words, limit t tends to infinity, e raised to power minus alpha t ft is must be finite. So let's look about this. So this function ft is continuous in subinterval 0 to 1, and this et here et e raised to power t is continuous in subinterval open interval 1 4, and also for 4 greater than 0 t is greater than 4 0 is a continuous function. So we observe that this is the subinterval t greater than 0 we can write 4 to infinity. Now in this interval ft is equals to 1 is continuous. In this subinterval e raised to power t is continuous, and this 4 to infinity 0 is continuous. So this is a piecewise continuous function. Ft is piecewise continuous function, and therefore the first condition is satisfied by ft. Now ft must be exponential order. What is mean? Limit t tends to infinity e raised to power minus alpha t ft must be finite. For example, suppose if we have given a function e raised to power t, suppose ft is e raised to power t, then limit t tends to infinity e raised to power minus alpha t et, and limit t tends to infinity is equals to e raised to power 1 minus alpha times t. For limit to limit exist, 1 minus alpha must be less than or equal to 0. If 1 minus alpha is less than or equal to 0, then for 1 minus alpha is equals to 0, e raised to power 1 minus alpha times t is equals to e raised to power 0t, and that's 1, and this is the limit is 1. And for 1 minus alpha is less than 0, e raised to power minus 1 minus alpha t e raised to power minus alpha t can be written as 1 over e raised to power negative of 1 minus alpha times t, and since 1 minus alpha is less than 0, so 1 minus alpha is greater than 0, so e raised to power minus 1 minus alpha times t tends to infinity as t tends to infinity. So therefore 1 over e raised to power minus alpha t tends to 0. So limit is finite in this case also. So e raised to power t is is of exponential order of if for alpha must be less than or equal to 1 minus alpha must be less than or equal to 0, that is 1 is less than or equal to alpha, or alpha is greater than or equal to 1. So e raised to power t is of exponential order for alpha greater than or equal to 1. Now let's look some more examples. So Laplace of tan t does not exist since tan of t is not a piecewise continuous function. Laplace of e raised to power t square does not exist because for the same reason e raised if we find out the limit t tends to infinity, e raised to power minus alpha t e t square, and this is limit t tends to infinity, e raised to power t square over e raised to power alpha t is not finite, since if we expand y is not finite. Let's look at this situation. E raised to power, we can here e raised to power t square tends to infinity, and this e raised to power t square is always greater than e raised to power alpha t. So this is much and more greater than 0 alpha t. So therefore e raised to power 1 raised to power alpha t tends to e raised to power t square tends to infinity more faster than e raised to power alpha t. Therefore this is not finite. Therefore this quantity e raised to power t alpha t tends to infinity. Therefore this is not of exponential order. Therefore, the Laplace transform of e raised to power t square does not exist. Now, we have some example. We have example of we have to find out the Laplace transform of e raised to power minus at. So, Laplace transform, definition of Laplace transform is 0 to infinity e raised to power minus st ft dt. So, this is the definition. We know, we have seen in earlier slides. Now, the Laplace of e raised to power minus e alpha t, if we put e raised to power minus at at the place of ft, then we have 0 to infinity e raised to power minus s plus at by dt. This is by the power rule. Now integration of e raised to power ax dx is equals to e raised to power ax by a. So using this is e raised to power minus s plus a t over minus s plus a, and limit 0 to infinity, and 0 to c where c tends to infinity. Now if we take limit c tends to infinity, e raised to power minus s plus a times t over minus s plus a negative, and this is e raised to power minus s plus a times 0, and this since it's c tends to infinity, here must be c, so c tends to infinity, therefore e raised to power minus s plus a into c into c is equal to e raised to power s plus a times c, and this tends to 0 because e raised to power s plus a into c must be tends to infinity. Therefore this is 0. So this is 0, and now this is 1 over s plus a times, and this is e raised to power minus s plus 1, e raised to power 0 is 1, so this is 1 over s plus 1. Thus we have calculated the Laplace transform of s plus 1 over s plus a. Now thus we have Laplace transform of e raised to power minus at is 1 over s plus a. So we have, so friends, today we have learned the definition of Laplace transform, the condition for its existence, and transform of some basic function e raised to power at. Now in the next video we will go deeper, exploring properties like properties and solving real examples. So if this video helped you, make sure to like, share, and subscribe to Let's Do Mathematics because we are just getting started on this journey. Thank you.